guys, and welcome to our lesson on Gibbs free energy. Yesterday our lesson focused on how enthalpy and entropy determine the course of a process. Today we're going to do two things. First, I need you to get your calculators because we are going to be doing a little bit of review and a little bit of math that I didn't do in yesterday's lesson to talk about enthalpy, temperature, and entropy of your surroundings. And then the second thing that we're going to do, and you'll need your calculator for this too, is to talk more about free energy, specifically Gibbs free energy, and how to calculate delta G, or this change in free energy, for a particular reaction or process. So grab those calculators. If you want to follow along in the textbook, we're on 573 and 574. So yesterday we talked about enthalpy and entropy and how they're driving forces for whether reactions are going to be spontaneous or favorable, or non-spontaneous or unfavorable. And we looked at 4 different scenarios, and most of the scenarios that we looked at, the reactions that were favorable they were exothermic. And exothermic reactions have delta H's that are negative. And that we've been talking about in this whole thermochemistry unit so far. We also talked about favorability as far as entropy as delta S being positive. So if we have a negative delta H, or an exothermic process, and we also have a process where the entropy is increasing, we certainly are going to have a spontaneous or favorable reaction occurring. And today we're going to look at a couple different reactions where we can use enthalpy, temperature to calculate entropy, or delta S, and we're also going to look at how to calculate Gibbs free energy, or that delta G. Now the equation that we're going to use to calculate delta S of the surroundings is a negative delta H divided by temperature. And we have to have the temperature in Kelvin because Kelvin temperatures are always positive. If we use Celsius and we have a reaction where the temperature was being done at a really cold temperature and the negative values, then it won't calculate correctly, and it will give us values that aren't going to make much sense as far as delta S is concerned. So we want that temperature to be Kelvin, so that temperature will always be positive and we won't have any negative values for temperature. So let's take a look at the reaction that I'm giving you here, and we're going to plug and chug basically into this reaction and determine if delta S is positive or negative, and if this would be a spontaneous reaction. So we are reacting antimony sulfide with iron, and we're doing a replacement reaction, and we get antimony metal and iron sulfide. And you can see everything is a solid there, so it's hard to tell delta S because everything's a solid. Nothing went to a gas or a liquid. We didn't have any phase changes. So we can't really make a prediction in this case just because everything stayed as solid. But we can see that delta H is a negative value. It's a negative 125 kilojoules. And what that tells us is that this is a reaction that is favorable in terms of enthalpy because delta H is exothermic, or the reaction is exothermic. So let's plug in these numbers and let's see what we get for delta S. So delta S, it's a negative sign in front of the reaction, or in the equation, and delta S is, or H, is 125 kilojoules. This is what happens when you do your videos later in the day. Your brain is not working. Usually I do my videos in the morning. And the temperature is 25 degrees C, but remember we have to add 275 to that, or 273. See, again, not working. 298K is what we're going to plug in. It feels like I'm just in the classroom. Okay. When I do the division here, I'm going to get a really small number, 0.419, and you guys can double check me. This is kilojoules per Kelvin, because I have kilojoules in the numerator, Kelvin in the denominator, so I'm going to have a unit with both of those in it. Now normally our delta S's are given to us in joules per Kelvin, so I'm just going to multiply by 1,000, and we have 419 joules per Kelvin. And so delta S is positive. That means the reaction's favorable. It means that there was an increase in disorder in this particular reaction. So if I look at enthalpy, the delta H value, it's negative, and I look at the delta S of the surroundings, that value is positive, I'm definitely going to be having a spontaneous reaction because both of those enthalpy and entropy are favorable. Now, just like we calculated enthalpy at standard state, we can do the same with entropy or delta S. You can use, now these delta S values, your textbook doesn't have them in the back of the book. So I have that thermodynamic data link on the class page for those values, and it's actually in the purple column. I think the last time we were using the pink column, so you'll want to check that to use for the delta S values to calculate delta S. So I actually brought the thermodynamic table up. This is the table that is linked on your class page, and we used the heats of formation, which is the pink column. You're going to move right over to the right to that purple column, and we're actually going to be using the blue column today too. So you want to have that handy so that you can look up values that you need to look up, not only for what we're going to do on this video, but also for your homework. So it's going to be important to have that available. And again, that link is on your class page. So for ease of calculating this reaction data, I've put the data down in the bottom left corner that we're going to need. And you can see that the S values at standard temperature, which is 298 K, and pressure 1 atm, is joules per K per mole. So just like we calculated the delta H, we're doing the same thing. We're taking the sum of the enthalpies of the products and subtracting the sum of the enthalpies of the reactants. So I'm just going to start putting in the data for you to see, and I'm going to do one reaction where I show you how we get rid of the moles and we end up with joules per K. So if you look at nickel 2 sulfide, we have 2 moles of that, so we're going to have a 2 moles, and we're going to multiply that by 53 joules per K mole. And you can see that the moles cancel when we multiply by the 2 moles, or that coefficient of 2 in front of the NIS. When I multiply those together, I get 106, and the units are joules per K. So I went ahead and I just did the math for the rest of the chemicals that are used in this reaction. I just want you to take note of the oxygen gas. When we talked about the enthalpy of gases at standard state, the diatomic gases, they had a value of 0. Well, that's not the case for enthalpy. So enthalpy values actually do have a positive value to them, which makes sense because they're gases. Some of the metals as solids are going to be 0 because they're solids, and so the enthalpy is really, really low, or 0. But for gases, we will see enthalpy values that are not 0. So now we're going to set up the calculation for delta S. So I have delta S equals, and I'm going to take the products first and add them together, 496 plus 76, and I'm subtracting that from the reactants, which I have 106 plus 615. And when I do all the math, I get an answer of negative 149, and that's joules per K. Okay. Now it's a negative value, so that means that this reaction is really not favorable, meaning spontaneous at room temperature, but it could be spontaneous at other conditions. If I increase the temperature, maybe this reaction would be spontaneous, but for the reaction that we're looking at, the delta S is telling us it is not going to be spontaneous as far as entropy is concerned. So there are the 2 ways that we can calculate the entropy values. Again, the entropy values you'll have to get from that thermodynamic data table on the class page because your textbook does not go into how to calculate delta S, but I thought it was important for especially those of you that are going to take a chemistry class in college. I thought it was important for you to see some of this math so that it makes a little bit of sense to you if you see it again in college. So now we're going to move our focus on to Gibbs free energy. So please keep that calculator handy because you can see right away on this screen there is an equation for delta G that we are going to use. And notice that it takes into account the delta H of a reaction and also the delta S of a reaction and the temperature. So we're looking here to see how much energy is available in a reaction. So this was named after Josiah Willard Gibbs. He was a physicist and chemist that was around in the late 1800s. He was born in the United States. He did live in Europe for a little bit of time with his sisters after his parents passed away. But he is originally from the United States, and he's pretty well known scientist, obviously, because he has something named after him, Gibbs free energy. So again, this is energy that comes from a chemical reaction, and it can be used to do work. And a good example of that would be, we've talked about this in the past, is your car's engine. So there's reactions that occur to make your car move and to make the engine work, and that is due to that free energy that's available from those reactions. So we're going to use the equation that's on the screen to calculate free energy, and again, it is dependent on the magnitude. Again, that means size of enthalpy, also the magnitude of entropy, and then again, we're going to be looking at the temperature of the reaction. Sometimes reactions are very temperature dependent, and if I change the temperature, maybe I'll release more free energy than if I kept the temperature at room temperature. So we're going to be looking at things like that. Now this slide just gives us a couple things that we need to keep in mind. All spontaneous reactions are going to release some kind of free energy, or that energy that's available to be used for something. If delta G is negative, then it's a spontaneous reaction because free energy is released. Free energy is not released in non-spontaneous reactions because non-spontaneous reactions, you actually need to continually be putting energy into the reaction for the reaction to move forward. But reactions that are non-spontaneous at one set of conditions might be spontaneous at another set of conditions. Like I mentioned before, if we change the temperature or maybe we change the pressure, we could change the spontaneity of a reaction. Now we're going to go through some typical questions about predicting enthalpy and entropy. Remember, enthalpy is delta H, entropy is delta S. So we're going to do some talk about predicting here, and then we're going to do some math. So the first question here, we're looking at methanol reacting with oxygen to form water and CO2. This is a combustion reaction because it's forming water and CO2, and the reactant is O2 that's reacting with the methanol. So I want to predict the sign of S. If I have more disorder occurring, then delta S is going to be positive. So if I look at what's happening in this reaction, you can see that I'm starting with methanol as a liquid, O2 is a gas, and H2O and CO2 are both gases. So if I look at the phase changes here, I have a liquid going to gases. So liquid to gas means that delta S is increasing. So my delta S is going to be positive. My disorder with these molecules is going to be positive. So delta S we would predict to be positive. The next thing that we want to do is predict the sign for delta H. Well, I told you that this is a combustion reaction, and we know that heat is given off as a product in combustion reactions. I can even write that in here. I didn't because I didn't want it to be too easy for you to answer the question. But if I predict the sign of delta H, because I know heat is going to be given off, delta H is going to be negative because it's giving off heat. And then it's asking if the sign for delta G is temperature dependent for this reaction. Well, delta G would not be temperature dependent because both enthalpy, delta S, and enthalpy, delta H, and entropy, delta S, are favorable. Like we said earlier, anytime delta S is positive, that's favorable. Anytime delta H is negative or exothermic, that is favorable. So if both of these conditions are favorable, it won't matter what the temperature is. So no, this is not temperature dependent. Heat will always be given off. There'll always be favorable. And we talked about this scenario in yesterday's lesson. So you can always go back and look at what is favorable and what is not favorable in terms of S and H. All right, hopefully you have those calculators handy. Here we have another reaction, carbon monoxide reacting with water to form CO2 and H2 gas. I give you the delta H values, I give you the delta S value, and I'm going to plug and chug into the delta G equation. So delta G, we know, equals delta H minus T times delta S. So I'm going to plug in these values. Negative 41.2 kilojoules minus the temperature we see is at 298 K, and my S value is negative 0.135 kilojoules per Kelvin. And I changed that to kilojoules, made that conversion because I need my units to be the same. So I changed the joules to kilojoules divided by 1,000. So that's why I did that. I need kilojoules so that I can subtract my two values. So when I do this math, I end up with negative 0.97 kilojoules. Because negative 0.97 kilojoules is less than 0, free energy is going to be released, and this is a spontaneous reaction. So because this is a negative value, delta G is less than 0, so it's favorable. Now it says calculate delta G at 700 K, assuming H and S are temperature independent. So let's see what happens when I put in 700 K. So I'm going to do the same setup, negative 41.2 kilojoules. But now I'm going to change the temperature to 700 K, and I'm going to use the same delta S value. So delta G is a positive value this time. So delta G is greater than 0. And because it's greater than 0, it's non-spontaneous. But maybe in reverse, at these temperatures, it would be spontaneous at 700 degrees K. Now I want you to take note of something. If this T delta S value is greater than the delta H value that we're given, that is going to tell us delta G is going to be positive. So if you look at, even though delta H is favorable, and delta S is not unfavorable, this is one of those times or one of those scenarios that we talked about yesterday where the combination of the temperature and the entropy is greater than what this delta H value is. So we could predict, in this case, that delta G was going to be positive because the temperature was so high. So the next question says, does raising the temperature favor this reaction as written? Well, we already said no to that. Raising the temperature actually made it less spontaneous. So the answer to that question would be no. And then it says, which factor, enthalpy or entropy, favors this reaction at high and low temperatures? So we said delta H is negative and favors spontaneity at all temperatures. And the negative delta S term is more important at controlling delta G at different temperatures. Delta H isn't going to change at different temperatures. It's going to stay pretty much the same. It's always going to be negative. So it favors spontaneity at all temperatures. But delta S is the one that's going to be more important at controlling delta G. As I raise temperatures, that's going to increase the delta S value. And when we do that, you noticed on the last slide when we did the math, I said that term T delta S was greater than the term for delta H, and so that's why it made the reaction turn to being non-spontaneous. So that's what that question's asking. And then the last one, it says calculate delta G at 315 K, and it says which reaction, forward or reverse, is spontaneous at this temperature. So you can see this problem's worked out at the bottom of the screen, and we get a delta G value that's positive. So this would be non-spontaneous, but in the reverse, it could be spontaneous at this temperature. But going forward, it is not spontaneous. So it says which reaction, forward or reverse, is spontaneous. It would be the reverse reaction. So just like we can calculate delta H and delta S at standard state, we can do the same thing with delta G. All three of these are state functions. If you remember me saying a state function was one where it doesn't matter how we get to the end state. If we take lots of twists and turns to get there, or we go straight to the end mark, it doesn't matter. We're still going to get to that final mark. It doesn't matter how long it takes or what path we take. That's a state function. So delta G can be calculated the exact same way. And again, you need the thermodynamic data link. It's that blue column that I showed you previously, and you can find that link on the class page for the delta G values. And the delta G values are in kilojoules per mole. So the only ones that are joules per mole, or joules per K mole, are the delta S values. So remember, these values are at 25 degrees C or 298 K. That's the temperature that these experiments were taken at to collect this data. That's why they're standard state. Okay, I've looked up all the values. I've written them underneath the molecules that they go with, and now I'm going to calculate delta G. And actually, I want to move that over a little to give me some room. So delta G, and that little degree sign means it's standard state, just like we talked about it with S and H. And I'm going to put my products first, and then my reactants. We're setting it up exactly like we would set up the summations for H and S. And so I have negative 457.144, that's the water. Whoops. And I'm adding that to a negative 394, which is the CO2. 394.359. And then we're subtracting a negative 50.72. And you'll notice that the gas is back at 0 at standard state for delta G. And when I do all the math, I get a delta G that's negative 800.783 kilojoules. Delta G is negative or less than 0, so it is spontaneous. And so that's how you calculate delta G. Again, exactly the same. You're just using a different column on that data table. And the last thing's your assignment. I already referenced the textbook pages, 572 to 573. There's a Gibbs free energy worksheet on the class page. You're going to submit that to the Dropbox. Please handwrite your answers. I don't mind if it's a picture or a PDF. It doesn't matter to me. And again, just a reminder that the thermodynamic data table link is on the class page to help you answer the worksheet questions. Hope you enjoyed that lesson on Gibbs free energy, and I will talk to you later.